Hi, everyone. Welcome to our fourth developer community meeting. Excited to have everyone here. Today's going to be a great one. Our tech lead, Simon Su, is here to present our SDK debugger, and he's also going to have an interactive session for us today. So our agenda today is brief. I'll provide just a quick developer community update, and then we'll let Simon go into his debugging CSL best practices presentation. So for everyone who wasn't in attendance in the last developer community meeting, I wanted to just share the slide again. We've recently launched our Discourse forum page. So if you go to discourse.cerebras.net and register, you'll be able to ask questions, see answers from us and the rest of the community. We also have a section for you to share your work and receive feedback from us in the community, and then also access latest Cerebras news. So please click on discourse.cerebras.net and hope to see you participate there. Without further ado, I'll pass this over to Simon, and Simon, you can share your best practices for debugging CSL.
Thanks, Uday, for the introduction. So today we are going to talk about the debugging our CSL best practices. We know that through previous releases, debugging is very important. So in today's talk, we want to focus on how to understand your simulation results. And if you have any hardware, your code have any failures on the CS2 or hardware failures, how do you go about debugging these problems? So the agenda for today is to cover how to use the timeline UI, which is on the right-hand side, and how to use this new tool that we introduced called the CS, the Cerebras Software Debugger, as well as the Cerebras Software ReadElf. And the goal of today's meeting is that I'm going to give you some personal hands-on experience on debugging designs that I came across, or designs that I personally had bugs, and what do I do and find those bugs and identify those failures. So with that said, I'm going to begin with some background to give us some terminologies and understanding of the acronyms and words that I've used. So wafer scale engine is defined as the 2D wafer that you see on the left-hand side. You can't really see in the picture here, but there's approximately 800 by 800 process elements. It's arranged in a 2D grid that you can see on the right-hand side. It's in a more abstract way. Each process element can talk to its neighboring process element through these interconnect, and they can talk to the 4 adjacent ones on the north side, the east side, the west side, and the south side and the west side. Each process element, sometimes referred as a tile, contains 3 components: the compute engine, which is the processor, a router, and the local memory. And these are important information because today's talk will be focused on debugging on the router and variables inside the memory. So that's what the focus of today would be. Now, how do we get our code on to run on simulator or running on hardware? Well, for any CSL SDK, the Cerebras SDK software, it takes in a minimum 2 files as input. The first one is the code.csl. This is the code or your own kernel that eventually gets programmed into the wafer scale engine. The second piece of code is a Python script, typically named run.py, and that's the host code. You do this by using a multi-step execution. The first is the compilation, which uses the executable CSLC. Now, I know this is compiling for simulator because I know that the fabric dimension is only 6 by 6. If this was compiling for a hardware, this dimension would have been a lot larger. Could be something like 800 by 800 or 800 by 900 or something like that. And then you do a run. To run the code, you execute the executable called cs_python on run.py, and you specify the directory that the compilation have targeted. So in this case, the directory is out, and you pass in -- name out. And I know this for the simulator because if you were to target this on hardware, there will be an additional parameter called --cm address, which stands for, and you pass in the address of the CM. Now the output of the simulation are the simfab traces, sim.log, and simconfig. There will be also the output folder. The output directory comes from the first step of compilation. Simfab traces are all the data generated by the simulator. Sim.log log that's written by the simulator. So unless the simulator crashes, I seldomly look at this log at all. And simconfig is not something that I'm going to cover today, but it's information about how the simulator was configured. Now, before we actually jump into looking at the UI, here's how you would load it up. So after you can load this up either after you compile or after you run the sim, and they will both work. And the UI supports Chrome, Firefox, and Safari. If you actually look at your work folder, you can actually use this command called SDK debug shell visualize -- artifactor. And the dot here means I want to load up the UI in the current directory. If you can also load up the UI by pointing to another directory, that's also possible. And it will return and give you a address, and you just copy and paste this address onto one of the 3 web browsers that support it, and you will be able to see a UI that looks like this. Is this enough, Rebecca, or should I keep going? Oh, if you're talking, yeah, you're on mute.
A little bit more, please. You were going for about 10 minutes before I noticed you had the camera off.
Oh, okay. All right.
And give me a little. Just do this. Just this slide should be enough.
Oh, okay. Now, in the terminologies, before we jump into explaining all the pieces in the UI, for today's talk, I will cover. These are the terminologies I'll be using throughout the entire talk. So a color means routing channel. Our device has 24 different routing channels. So you can imagine there's a 2D grid, and then there are 24 layers of routing that sits on top of it, which data can communicate between PEs. Wavelets are actually a 32-bit data that travels between PEs. So that's what a wavelet is. A task, which I won't go into it too much, so you can think of it like a function. So a function will get called when a wavelet arrives on that particular color. When a task is being invoked, it will execute instructions, and the instruction is the lowest level assembler our process element, our compute engine actually runs on. Now, data are sent back and forth from the wafer scale engine to the host through I/O tensors. And finally, memory data are data that gets written into the memory oftentimes it's before the execution starts, or it can be read back after the run.py is completed. So that's what memory data, and we can access these memory data directly from the host, and that's how we write and read to it before execution and after execution, respectively. So here I've shown a very simple diagram of inputs that a router have inputs from all four cardinal direction, as well as the process element, and it can output to all 4 cardinal directions or to the process element. And when it enters the compute engine, it will trigger a task. So in order to trigger a task, you have to bind a task to a particular color, and that's how it will work. So when a wavelet is coming, it's arriving on a particular color onto that particular PE, that means then the compute engine would, that particular wavelet would enter off the ramp into the CE, into the compute engine, and the task will start executing on that particular wavelet. So for today, in order to talk about, I said we're going to talk about something that's concrete, something that's hands-on. I'm actually going to walk everybody through a real design. And this is the GemV that I've picked. It's easy to understand. It's something that also everybody have. It's shipped with our SDK. You can find the GemV benchmark under example or CSL example, benchmark GemV. The way GemV works is that it has a output tensor, which is Y, and that's computed by doing the following operation: A times X plus B. And the way the code is set up is that A gets initialized once during the entire execution, and it's inside the memory of each PE. So the entire tensor is being distributed across a 4x4. The input X is being streamed in from the north side. The input B is being streamed in from the west side. The way the math and the output finally is being streamed out to the east, and then that goes back to the host. So let's look at how the CSL code is written for if someone ever wants to write this type of computation. So in here, you have the GemV code where you can see the CSL code in the middle. The way the computation works in pseudocode wise is that you first compute a temporary variable called AX, in this case called AX temp. AX temp is equal to A times X. And then you take the output, which is Y, and it equals to out, and it's equal to AX temp plus B. So you can see here these F multiply and floating point add. And that's what that is, these two functions, and they bind to these tasks. So that's how it works. Then let's look at what the host code looks like. You can see here, what we do is inside the code, you see there's something called set symbol rectangle. What that does is it allows to initialize the value of A before the run starts. So you provide this initialize what this A value looks like throughout the entire execution. Then the second and the third thing it does is it sets up these input tensors. So you see here, add input tensor is sending in the value X on a particular color X, and the user picks what that color would be. B would come in from a different color, and finally Y is being on the output on a different, again on a third color. So you can see here, X is actually using color 1, B is using color 2, and out is actually using color 3. So you can see here, the UI actually tells you what you've done, and you can use that to confirm whether that's correct or not. And finally, all the output can be read back using this runner.out tensor, and you can see whether the result is what you expected. So the takeaway here is there's add tensor, set symbol rectangle, which is for copying initializing the memory, and finally you get the output using the API out tensor dictionary. So before we jump into the UI and actually run a simulation, which I'm going to do after the slide, I'm going to break down the UI for you and describe what it does. So in the UI, you will see there are 3 distinct sections. The top brownish color is the menu. It has the most important thing is the setting. We also have a dark mode in case anyone is interested in the dark mode. In the middle section, you have the user is the control section. You're controlling which color you want to view your data, and what is the grid, which PE you want to see the data. Now I'm gonna pause here. Instead of describing fully what the timeline pane looks like, I'm actually gonna run the sim, and I'm gonna show click through the UI and show you what it looks like. So here I have already started let me start a brand new run and show everybody what that looks like. So I have 2 terminals here. You can see 1 and 2 at the bottom. I use 2 terminals very often. That's how it makes it easy to debug. So when I'm running something, compiling something, I'm on one of the terminal. And in this case, you see that I made a little script. This script is very simple, nothing more than what I just mentioned earlier, which is the cs_python, the run.py -out. Sorry, I think it's -name out or something like that. Yeah. So yeah, I'll just show you what that looks like. I just made a script so I don't forget what I was going to do. You see here, this is the command I'm running. That's all. I'm skipping the compilation. It's for the interest of time, but that's yeah. So let me go ahead and execute the script. So we'll give it a second. When the script runs, it will run the simulation. It will set up the tensors. It will, like here, program the fabric. And I have intentionally made a pause here, and I'll come back why I did that. Now, in order to launch the UI, I will use my debug terminal, which is over here. I have the command here called SDK debug visualize, and I've put in in this case, I'm not in the same directory, so I'm going to put the actual path of where that runs. So it'll look something like this. So it should take a second, and now it will tell you what the address that you want to look at your results. So let me open that up. I will enter in the new one. So you see here, when it loads up, it only shows you the first top 2 pane that I mentioned, right? So the top 2 pane here is the first one contains settings and dark mode. So that's what dark mode looks like. For today, I will just keep it in the light mode. The setting is one of the new feature that is fairly important. And I'm going to click on this and show you what that looks like. So this allows the design of the setting allow the user to have one page, but they can load up any previously compiled directory or run directory they want, and they can toggle between them. So if you have multiple compilation, you can actually load them up in this view. So you can see here, it was able to find that I have one output directory, out.sim. It's able to see that is my current run directory. And it knows that because it knows that's where it contains the sim trace directory. And it also has the option to let you see what your final routing looks like. So when we finish the simulation, we actually output a file called core.out. This is an optional file. If you don't provide this file, I'll show you what that looks like in a minute. And finally, where your source directory. So if we need to map things back to your source directory. So this allows the user to pick different simulation. If in your work directory, you have multiple simulation runs because you're tuning around, either you're tuning your CSL code and you want to recompile, but you don't want to overwrite the previous one. This will find all your compilation directory, and you can load up one at a time. You can pick any one that you want to load. So with that said, now let's use this UI and pick how to load up the timeline. And then I'll go into explaining what the timeline looks like. So first you click on timeline. And now this allows the user to pick which channel you want to look at. So if I want to look at, which color you want to look at. So if I want to look at the input, that's X, you immediately see the routing that's coming from the north side. And it goes vertically all the way to the bottom. And if we inspect the first wavelet, which would be this one, you can see now the timeline view automatically pops up. Now the timeline view, it's divided, it has a number of controls. So you can zoom in, you can zoom in and you can zoom out. Sorry, had that reverse. You can, when you zoom in, you can use this bar to control where you are in the time. So horizontally is time. And the vertical here is which PE and the color that you're looking at. We can keep clicking through and it will keep adding wavelets on the UI. So the way you look at, okay, so I hit an error. So this happens from time to time. This, if this happens to you, like me, you can just refresh and just load it again. It should, it will work. Yeah. So, yeah, okay. So that didn't quite work the way I thought it would. Okay. You see why that's the case? Wow. Okay. So something's gone wrong here. Okay, I'll take notes and we'll come back and fix that issue a little later. Yeah, I'll make note of that. Yeah, so you can see here, you can see we also sort the tiles that's being inserted into the timeline. What you're looking at here are individual wavelets, the data that's propagating through your fabric. So you can see here the first wavelet that's going through starts from the north and it contained the value 35B5. And this is the debug pane that shows you what that wavelet contains. It's sending from, starts at clock cycle 185 to 186. And then it goes to the adjacent PE, which is the one at the bottom. And it goes from at clock cycle 186, and it's the same wavelet. Now the next wavelet that's being sent from the host to the north edge is this one. And in total, we send 4 wavelets. And to terminate the sending, we send a control wavelet, which is what this blue color means. So blue color is a sentinel wavelet, which we send at the end to denote that this is the end of the tensor that we're sending in. So let me go back to the slides and explain now. So this slide contains what you're looking at, the timeline, the router information, the zoom controls, and the debug pane and the values. So now let's talk about the interactive demo on what I've just shown you, right? What you're seeing is wavelet propagating through. So why are those important? Well, there are actually 3 important use cases, and I'll go over them right now. The 3 cases that you're looking at is the importance of knowing the start and the end cycle. I use it to debug missing wavelets and orphan wavelets. So let me go back and show you how that's done. So whenever I'm looking at the start and the end cycle, what I want to get is when is the first wavelet coming in? And in this case, I know it comes in on this particular PE. And let's look at where the outputs are. So the output would be the Y, which is what this is. And I know that the last wavelet exits from coordinate 4, 4, which is right over here. So if I click on that, you will see, and I zoom out all the way, and you can see the beginning wavelet comes in here around clock cycle 185, which is what we were looking at earlier, 185. And the last wavelet exits right over here. And now you notice it takes up more than 1 clock cycle and it's coming up red. And I'll explain that in a minute. You can see the whole entire processing takes about 1,800 clock cycles, right? You take this last number and you subtract by 185. So that's how efficient or inefficient this design is, you can say. The entire processing takes approximately 1,000 clock cycle. You can see what's happening when we're sending out the data. When we finish computing the data, we're actually sending 1, 2, 3, 8 pieces of data out. But towards the end, what's happening is the last 2 data is actually getting delay. It's getting back pressure, to be exact. So what's happening here in these red wavelet, it means that when we're about to send out the second last wavelet, it is getting back pressure by the adjacent PE. It means that the adjacent PE is doing some processing, or either it's doing some processing or it's trying to send or it's being further back pressure by where the data should eventually go. So therefore, this data cannot be sent out to the output. And we can click through this and figure it out, what that would be if you're actually debugging this problem. So that back pressure means this PE is sending the data to the adjacent PE, but the adjacent PE is busy for some reason. So it cannot receive that data. And this is one way that we can identify using the timeline to know where certain inefficiency are in the design. So in this case, yeah, approximately 300 clock cycle is essentially wasted on because there's delay, because the destination cannot receive the output. And the total computation is approximately 1,800 clock cycles for the entire design. So that's what I use for using the timeline. The other places that I use the timeline is I call these missing wavelets and orphan wavelets. So now I'm going to go back to my terminal and I'm going to explain why I have a pause here. So one of the features that's very subtle that we've done in 04 is that you don't have to have the simulation finish before you load up the UI for debugging. And that's not true for 03 on the previous versions of the UI. In the previous versions, the simulation have to complete successfully before the user could actually look at the UI and actually start reason about it and debug what's happening. The whole intention here, what I'm mimicking, is that if you're, for some reason, one reason or another, that your simulation has hung and it's not working because you have for various reasons. It could be, what I came across could be accidentally you have an infinite loop in your routing, or your wavelet got drop. So these are what I call orphan wavelets. So accidentally your routing is incorrect so that some wavelet did not get to the destination. So those are, I call them orphan wavelets for today's discussion. You can then, at this point, your simulation will hang just like the way I show it, but you can now load up the UI. And when you load up the UI, you can start tracing through. You can use the timeline view to trace through where your last wavelet. That is one possibility. I'm going to show you another feature that's useful for debugging this kind of hang. And that is, if you unclick this timeline and you want to look at what's happening with my wavelet, what is my last wavelet being sent, you can click check the color. You can go to this wavelet trace, which I use it very often to debug these orphan wavelets or infinite loop. You can click here, you can select hexadecimal. Now this loads up the entire wavelet, all those 6. In fact, I maximize this, all the 8 wavelet. I look at the last one. I look at the last wavelet. Is this the particular data I'm expecting? We can change the format to F32. Yeah, you can see if this is the correct decimal. I think we're actually doing floating point 16. You can see if this is the correct decimal that you're expecting, so that you know where in simulation where that hang came from. Now, as I mentioned earlier, what happens if I have infinite loops or missing wavelet? Well, I won't be able to see this, right? Like, how do I find that out? If I have an incorrect routing, how do I see this? So I'm going to show you a feature that we also put into the UI where if the simulation actually didn't finish, what will happen is this core.out wouldn't exist. So let me delete that. That was from my previous run during practice. So I'll save the setting. What you see is suddenly there's a lot less color. What's happening is that it's actually loading before any run occur. What you wrote in your CSL, what the routing would look like. And I'm going to select all of them. And you can see, is this your expected routing? So even before a run, just a compile, you can just load up the UI, just like the way I did it. And you can debug, did I actually wrote in my CSL the routing I expected? And I've done this myself. I also seen in other places where yeah, people create infinite loop. Like so, so you have routing that goes in the loop and it never exits. So yeah, that will result in, and those are mistakes I personally have done as well. And that will cause hangs and things like that. And now you can use the UI and just look at your CSL code. Did I create my routing correctly? So that's another feature that you can use for even before running. You can debug your compilation. You can debug your CSL routing. So those are the features I want to share in the how to use the UI to debug the simulation, all that new feature that we've put in. I'm going to summarize by explaining all the different things that you can see in the timeline and what they mean. So if you're looking at the timeline and you see wavelets being active, that's great. That means that the PE, the data that you want to send to your destination PE, is getting sent in the correct time. There's no back pressuring, there's no delay. That's great. That's what you want. If you're getting back pressure, which is the red, that means whatever data that you finish processing and you want to send to the adjacent one. The adjacent one is saying, I'm busy. I cannot accept your wavelet yet. So that's what back pressure means. And the way this happens is that you can have, because you may have too much processing going on here, you might want to distribute your computation a bit more, so you can be sending what you want to do is balancing between computing, meaning you should distribute how much you want to compute per processor and how much data you're sending, right? So that's one way to use the back pressure information. So here I created a diagram where I created lots of back pressures, and you can see it's because I'm making it too busy. Delay, this middle one that I didn't show in today's example, delay occurs when situations where a PE is trying to broadcast their output to multiple PE. So when you're trying to distribute work, oftentimes I've seen a design pattern where you have a column of PE or one PE that's generating data from multiple PE. So one PE is fanning out to 2, 3, 5, or 10 other PE to do work. So when you're broadcasting information, broadcasting wavelets, often what happens is you can create congestion in the router. So when the router is congested, you cannot actually send data through. You have to wait for the router to send what it currently have, finish sending that, and then the other wavelets. And that's what delay means. Now, this final one that I'm not going to touch upon too much is idle. So it's less important for today, but the idea is that you see these sparse moments where you're sending data. What I've come across is we have situations where we're not sending data fast enough, so it's sitting there idling, doing nothing. So the UI can give us this sort of insight on, am I creating congestions? Am I doing too much computation and is back pressuring? And of course, if you're not doing enough, that's what it means by you're idling too much. So there's too much gap between the greens. So those are the patterns that I personally have come across. Before I switch gears, are there any questions online that I can answer that you may have on the UI? Let's see, there's nothing on the chat.
Simon, I'll ask a question if no one
Sure.
else does. Just for my education here, is the purpose then of these visualization tools to help you understand how to have wavelets flow with no delay or back pressure, and then at the same time with have no processor be idle? Like ideally, you want just constant flow, right?
Yeah, that's right. In the ideal world, what you want is have your computation do work, send in the wavelet, do work, send out the wavelet, right? So now you're keeping the router, you're trying to keep your processor as busy as possible, but not so overloaded where you're sending things and outputting too sparse, right? So otherwise, that means your processor is way too busy and you're putting in too much computation into one processor. So you notice that in the design, we're only using a 4x4. But the way I typically do design is that I would first make a small tensor, do an operation on a very small grid, so I can see in simulation how much computation, how congested my router is, and then I scale up. Because once you scale up, it takes longer to do simulation. It's not always easy to observe what's happening. But what you want is, if you're scaling up linearly, what you're observing in terms of idle occupancies, those values don't change, right? So what I do is I use these timeline graph to understand, am I having too much congestion or back pressure? And as soon as I get to the point where, okay, I don't see a whole lot of red, I'm actually using as much processor as I want. I'm not putting all the tensor into a 2x2. I'm spatially spreading them in a way where I'm using all the processor and not creating too much congestion. Then what I do is I scale up my tensor and I put it on hardware. And that's how I do. That's how I scale up the design. Yeah.
Okay, Simon, we've got a question from Emin. Sorry, Emin, if I'm mispronouncing that. You said on the router, only one wavelet can pass through at a time, right? Let's say if we have two wavelets, first one's from north to south and the second one's from west to east, then these cannot pass on the router at the same time?
Yeah, so Emin, that's a great question. So the mental model you should have is that there is only one wavelet can pass through the router at a time. That's the easiest mental model you built up. So if there are two arriving at the same time, which is what you mentioned, the first one coming from the north, another north to south, another one coming from west to east, and if they're on the same color, the router will pick one to go first and then delay the second one. Okay. So here, if there's one going from north to south, another one going from west to east, and they both come in at the same time, the router will pick one of them and pick it to go first. I don't actually know which one will go first. I typically use the simulation to figure out which one will go first. But yeah, so what will happen is, let's say in your example, north and south, the router picks north, south first. Then what you see is that the wavelet from west to east will be yellow. It'll get delay. And that's where the yellow one comes from. That's what that delay means.
Simon, follow up for my benefit. That delay you'd expect to be like one clock cycle or what?
In this example, yes, it will be one clock cycle. Yeah, that's right. Now, let's make this example a bit more complicated, Rebecca. That's a great question. Let's say now the router picks north to south goes first, but it gets back pressure in this one, right? So this one will get delay as long until this first one gets resolved. That's what will happen. So if this gets back pressure and it cannot go into this particular PE for 5 clock cycle, then this would get delayed by 6 clock cycle, and that's what will happen. Yeah. And our UI also differentiate between delay and back pressure. So let's extend that example a bit more. Let's say the north goes to south. That's no problem. That's 1 clock cycle. So then this here, you would have a delay of 1 clock cycle. But now, when it's trying to go to, it's from west to east to the PE on the right-hand side here. But then this PE says, I'm busy. I cannot accept this wavelet yet. Then what you see in the bar here is you have 1 clock cycle of yellow, followed by as many clock cycle of back pressure as it needs for this processor to process that particular wavelet. Yeah, so great question, yeah.
Another clarification, Simon. If the north to south was a different color than west to east, would it also delay would they also delay each other, or could they be sent in the same cycle?
Thanks, Justin, for asking that question. The congestion only occurs if they were the same color. So one way to resolve these congestion is by using different colors. So that's another technique that's very common. Using different color to resolve it is probably the easiest way to resolve these congestions. It is also, I do want to mention that there's only 24 colors. So you have to plan out what color you use in advance. And that's typically one of the more challenging design work to make a high performance kernel. Okay, I'm going to switch gears to show everybody how to use debugging on hardware. So we spend a lot of time looking at what the simulation, what the UI looks like. So now we can scale up the design. We're going to put this on hardware, and we're going to see what actually happens. So in here, what I've done is I have another 2 terminals where I am on the coordinator on one of them on the machine that actually talks to CM, and in internal term we use the word coordinator. So in here I already have a run. Again, I paused it at the right place, and here you can see it's actually running on hardware. The dimension is a lot more. It's 756 by 830. When it hangs on hardware, like the way I've shown here, if it does hang, you have another tool on hand that can help you, and it's called CSDB. So here I will go to another terminal, which is the debug. And what I do is I start up another executable called CSDB, and you start it up this way. So you type CSDB, you specify the work directory, and here I already done that. And I'll show you how to do that in a second. And you use the command to use the context command to select what compilation directory that you want to use. And there's a target command that you specify the CM address. So now what you're doing is you're asking, I want to do some interactive debugging on the actual wafer scale engine on the CS2. And you can specify the rectangle, the PE region that you want to debug. And with those, you can now read out the memory, the local memory. And you can see here in the screenshot I captured, I'm using the memory read command. I'm reading address 0. I'm reading 32 addresses, each one of them being 2 bytes. Now the trick is, well, how do I know what addresses I want to read? So now I'm going to introduce you to, I'm going to go off tangent a bit and show you another tool that we have actually built in 04. It's called the CS-readelf. So let me first show you what this tool does. This tool helps you understand when, after compilation, your variable turns into symbols. If we're actually trying to debug A in my design or AXTemp, you see that these actually turns into symbol, and in using this tool, you can see what address and what's the size these variables are inside the PE. So one of them is address 0, another is address 40. So let me actually show you what that looks like. So if I go back to the terminal here, what I'm going to first show you is the CS-readelf. So in CS-readelf, oftentimes I don't remember the command, so I just type help and figure out what I wanted. So in here, I know that what I want is to read the symbols. So I'm going to provide --sims, and I know the location that I wanted, which is CSL example, benchmark, GMV, and it's in the output directory that I'm looking for here. Inside the output directory, I'm going to pick one of the output. So one of the L file like this. And if I do that, it will tell me, yeah, here's the memory. This is what I want. And these are the address. Now, if I want to start a CSDB session, which I said I was going to show you how to do, it would look something like this. So here I'm starting a debug session, which is the tool is analogous to GDB. Instead of attaching to a process, instead you point to what work directory you want your output. So now I'm starting a debug shell. You can see here, I can see if I type settings, it will tell me here's the work directory. If the work directory contains only one compile, then it will automatically find the compile folder and load it automatically. If it contains multiple ones, then you have to pick one before you continue. Notice there's no target selected. Okay, I'm going to show you a neat trick on how to do interactive and non-interactive. So if you're doing interactive debugging, I will go back to this terminal. And this is doing interactive debugging. And if I scroll up to the history here, you can see here, I have created I'm targeting a CM address. Now, what I could do is that if I'm sharing a machine with a colleague, but I want to know why my design hang, one of the common things I do is I take a core dump of the entire wafer. And the command to do that is use save core. When you do save core, it will create 4 files. These core files, .gz, 0, 1, 2, 3. We've broken them up because the wafer is so big, so we've broken them into 4, so they're manageable. It takes around, you can say, I'm going to roughly say this is about 3 minutes to take the entire core dump of your wafer. And at that point, you can use target list and it'll show you, yeah, I found this particular core dump in there. And at this point, you can log out the system. You can copy all these files back to your own personal machine and continue debugging, which is what I'm going to do right now. I have already taken all the files back to my own personal machine, so I'm not taking up the machine time. Other people can continue using it while I spend my time debugging why the hang happens. So I could go back here. If I do target list, you will see I have the core file that I have taken. I will then say target create. Again, if I don't remember the command, I'm going to go --help. I do target create. And in this case, what I want is the core file. And I'm going to do a shortcut where I'm just going to use 0. You can type the whole path here, or you can just use 0. I'm just going to be lazy here and use 0. And now I have selected the core file as the thing that I want to target to debug. So I'm actually doing a post-mortem debug. I don't actually have the machine. I'm on my own local machine. So these are all possibilities that you can do. Like, it's essentially the same thing. If you want to stay in the machine and debug the hang, that's absolutely fine too. Here, the rectangle is the entire wafer. It knows that because my compilation tells me that I'm targeting a 758 by 900, 757 by 996. But because I know my design is a 4x4, I'm just going to save time and do rectangle. I'm just going to use the rectangle command to select a much smaller area to debug. In this case, the command is right here. I mentioned it earlier. You can use the rectangle command to describe the offset, the width, and the height. So in this case, it's 1144 because that's what my GMV looks like. So I'm just going to quickly go back and show you. Yeah, this is what my GMV looks like, right? It's offset to 11. My code is in 44. So I do that. I confirm that I have selected everything I wanted. Now I can use, if I type help, for example, I can see all the different commands. If I want to use, I am going to use the memory command. And I'm going to read the memory. And because I was using the csreadelf command, I figure out that, let's say I want to read the value inside A. I want to read the first, let's say 4 values of A. So what you would do is you would do -A stands for the address on address 0. And then the length that I want to read is 4. Oops, sorry. And if it hits enter, it will actually generate all the output to this log file that you see here when it's done. It takes a couple of minutes to do that. But all the output, you can find it in this particular log file. So yeah, so there are a lot of other, so with the combination of saving the core, csreadelf, the memory command is very powerful when you're debugging on hardware. So when it hangs, for example, if I can't figure out where the hangs are, I would go to my CSL code. I create a temporary variable, and at different places, I change the content of that variable. that debug variable, and I can read the content of their variable and figure out where am I in the code that got hanged, right? So that's one thing that I do. So you can see here it generated the output into this log file. I'm going to go back to my run terminal and look at what that looks like. Okay, so let's go back to my pretend hang in my hardware run, which is in this folder. You can see I have a log right here. I'm going to show you what that log looks like. So you can see here, it will tell you that it uses, it took a few minutes to run all this. And these are the values. You can see here from PE11, address 0, these are the 4 values that I read. So I can check if compare against whether on the runtime did I actually initialize the memory on A, are these the correct value? And that's on the host code, right? Like you can print those, I could print those values out, I can compare them. I can check if they're for functional failure or debug hang using this method. So yeah, so just to summarize and some terminology here, the compilation directory, which is called the context, that's your compilation directory. By default, the name is out. You always have working directory. That's where all the output writes to, like whether it's a log file, which is what you saw. The target command is one of your favorite command. If you're doing interactive debugging, you set the CM address. You can save a call, and if you're sharing a machine, you can't be on there all the time. You can save the call file and bring it to your own machine and do any post-mortem debugging without the CS2. And that's very useful for debugging hangs. Like right, when you get hang or on CPU, it's the same, right? If you get a crash, you have a core file and you can load that core file into GDB. It's a very similar concept. Lastly, this is the last slide. I'm going to conclude today with remind everybody that we show everybody the visualization. The different, you can see how wavelets are traveling through different PEs. You can see how long it takes to propagate through the entire wafer scale engine. And you can see the debug raw values of these wavelets, whether they're correct or not. And secondly, once you got all that working and you want to scale up your design, you want to see if it works on hardware. So on hardware, you have these two, you have the tools called the debugger. And if it work conjunctionally with the readelf tool to figure out what addresses you want to read, you can read the memory, you can take a core dump of the entire wafer for debugging. So those are all the new tools we introduced in this particular release. We work through some of the problems. I've worked through some of the problems myself to debug, especially hangs. Like this is what we're targeting to enable user be able to do, and we've seen those time after time. So that is all for my presentation. Are there any questions?
Looks like you were perfectly clear, Simon.
Great.
Awesome. I think, Simon, yeah, this was great. Really appreciate it. The interactive session was really helpful. And for anyone in the audience, if you do have questions that come about later, you can always reach out to us at, developer@cerebras.net, or I'll paste it again here. Posting your question on our discourse is another effective way to get us to provide you with a response.
Right. If any community members have maybe ways around people's problems, if they happen to be on discourse, they could chime in. That'd be great.
Yeah, that'd be really great. Awesome. Thank you, Simon. Appreciate your time. Thank you, everyone, for joining, and hope to see you all at our next developer community meeting.